In this video, we're going to talk about section 6.3. So we're going to really look at some different types of formulas with money and interest type problems. Some of them are going to be using integrals. Some of them are just going to be using formulas that you've seen in previous sections. So the biggest difference is going to be really when you're reading the scenario and being able to identify what type of formula you're going to use. So for these first few examples, we're going to look at what's our total value in the end, or the future value of an account. So for this first example, we're going to be using this formula here. So this is the accumulated value of a non-interest earning stream. So basically, if you ever have a situation where it's talking about money going into an account continuously, that indicates an integral. And the other important thing is that there's no interest. So it's a non-interest earning account. And then you're going to be using this formula right here. So if we look at this first example, it says revenue flows continuously. So continuously means it's going to keep going into this account. And here's our function that we're going to use. Here's the rate that it's going into this account. So basically, in this case, since it's a constant function, it's just adding $128,000 per year into this account. And then as the money is received, it is placed into a non-interest earning account. So that's important because that indicates we're going to be using this formula up above. We want to know how much money has accumulated in the account at the end of a 3-year period. So basically what we're going to do is we're going to integrate from 0 to 3. So that indicates here that we're going to integrate from 0 to 3 years. And again, the reason why I know it's an integral is because it's continuous money flow. So it's money that's going into an account over and over. So let's kind of identify these. As I do these problems, I'm just going to kind of write to the side how I know what formula to use. So this is a continuous money flow without interest. Those are the key words here. So that indicates I'm going to use the formula from up above. So from 0 to t of f of t with respect to t. So now if we're trying to find the amount or the future value, we're going to integrate from 0 to 3. My function here is 128,000, so it's just a constant. And then we go ahead and we just do a regular integral. So from here, it's not anything new. It's just setting it up as the new part. So when I go to do this, the integral of 128,000, or the integral of a constant, will always be that constant times t. And then I'm going to be plugging in 0 and 3. So I have 128,000. 3 goes in first, minus the 0. And again, in this situation, that 0 is just going to go away on this side. So I end up with really just 128,000 times 3. So we're talking money, so $384,000 is what the account would have. Now, you could have figured out this problem definitely without integration, because you could have just said, okay, if I'm putting in $128,000 per year for 3 years, well, you just do 128,000 times 3 and you'll get your answer, which, if you look, that's exactly what ended up happening. But this is just a situation of what happens if your function isn't a constant, or you have some kind of different scenario where you would want to be able to use this. So that's the first one. The next one, we see this formula is for a one-time lump sum interest earning investment. So that means you're only going to put money in once, and then it's just going to sit and grow. So see how this is not an integral, because you're not constantly adding the values together. Integrating really is just the accumulation. So you're adding up the values that you keep putting into the account. So in this case, I'm just looking at a one-time lump sum, and it's just going to grow on interest. So you've already seen this PERT formula. So your amount equals your principal, or the initial amount you put in, times E raised to the rate times time. So let's go ahead and look at this one. So here's our example. And you're going to see very similar investment. So we're doing $128,000, but the key words here, it's a one-time lump sum, and it's going into an account that's paying interest. So the fact that there's interest tells me that I have to consider that, which means I have to use the formula from up above. So this kind of problem I would classify as a one-time investment with interest. So it's not continuous. You're putting money in once. So that indicates we're going to use our PERT formula. So the amount is going to be your initial investment, so the $128,000, times E. Remember, E is just a number. This rate is going to be as a decimal, so 0.07. And now for 3 years. So then 3 is your time period. And then we would just type all that into our calculator, and we get $157,910.79. And again, we're rounding 2 decimal places because we're talking money. So that's it. So now you've seen one where it's a one-time with interest, and you've seen one where it's continuous without interest. So next we're going to look at continuous with interest. So if we look at this scenario, it's kind of, so let's just kind of read through this problem here. So suppose that at the end of each month, for 6 months, $100 is put into an account paying 6% annual interest. So we have interest, and we have, for 6 months, we have $100 into an account. So this indicates that it's continuous for 6 months. And then it says, except for the last $100, which earns no interest at all because it was just put in at the end of the month, or at the end of the 6 months, each $100 earns interest over a different period of time using the continuous compounding formula. So using what we just talked about in the last problem, how could you solve this problem? And then also keep in mind here that since the interest is 6% annual interest, we're looking at monthly because we're talking about 6 months. So basically we're going to take that interest and we're going to divide it by the 12 months. So this is going to be your monthly interest rate. So if we, this is a typo too, you can fix that, money. And then if we just kind of look at this, I didn't want to do this problem with you, I just wanted to kind of show you what would happen because this is kind of a very long approach to something that could be done much easier. But I wanted you to kind of understand the math behind what's going to happen when we use integration. So for this, we're using our PERT formula. So remember, this is for a one-time lump sum interest earning account formula. So basically, if we use that, well, that means, okay, we look at the deposit on the first month. We put $100 in, so there's your one-time investment. That means after it can get interest for 5 months, because it went in at month 1, there's 5 months left for it to be able to get interest on it. You're going to get $102 from that investment. Then if you look at another on the second month, okay, well, now we have another one-time lump sum investment of $100, but that's only going to earn interest for 4 months because it was deposited on the second month. So here's that. You get $102 from that one. Then the third month, you put $100 in, one-time investment. Okay, well, that's only going to earn interest for 3 months, so you get 101. And then you basically just continue this process. So if you look at each of the individual deposits for the 6 months, you add them up. So you're basically looking at each of those deposits as, here's the one-time lump sum, here's how many months it's going to earn interest. And that's how we're using that PERT formula. So this represents, you add those up, this represents the total amount. So you can probably already think how this could be a nightmare of a problem if, let's say, you wanted to look at 20 years, right, or 100 years. It could be a nightmare because you'd have to find each of those individual amounts and then add them together. So luckily, the question here is there a shorter method to finding the future value of an annuity? Yes, there is. We can use integrals. So that's kind of how this is tying together. So we can use integrals. So that means instead of using our one-time um, investment formula with interest, that PERT formula, we can use integrals. We can integrate that formula. So here's what it looks like. If you want to find the future value in an account or the amount at the end, you can use this formula here. And if you look at this formula, it's almost like that PERT formula that you're integrating. The only difference is this is can be written as a function. So it might not be constant. Most of the time you're going to see it as a constant though. But that's indicating the rate of flow of money into an account. So that's that continuous deposit that you're putting into an account. And everything else, you can it's basically the PERT, and then you're integrating with your time. So let's go ahead and look at an example. And this is what we would consider a continuous money flow with interest. So that's kind of combining what we saw. So we saw for the first problem with integrals, you use it whenever it's a continuous money flow without interest. And then we saw a one-time lump sum with interest was that PERT formula. Now we're kind of putting those together, because what happens if you want to have a continuous money flow with interest? So that's where this comes into play. So let's go ahead and look at an example. Basically, we're going to look at the example that we just saw. Where you saw it worked out using the old method or a long method, we're going to use this formula. So we know that, first of all, it's a continuous money flow problem with interest. So let's start with writing our formula. So our future value is going to be the integral from 0 to t of f of t times e to the rt with respect to t. So we have, if we go back to the previous page, we're putting in $100 each month. I'm just going to kind of write this stuff down. For 6 months. And we're looking for the rate. We need that as well, because we know the 100's going to go here. We know the time period's going to be 6 months. And we need to know the rate. So remember, the rate that they gave us was an annual rate. So let me just kind of write that out. So the annual rate going back was, I'm just going back to the previous page here, was 6%. So 0.06. But we have to find the monthly rate, which was already done on the previous page, but just to kind of show that again. So I'm going to divide that by 12. So my monthly rate is going to be 0.005. So you're going to see that that's going to go into my formula here. So let's go ahead and start plugging in. So remember, this is a continuous with interest problem. My time period here for the saving is 6 months. So from 0 to 6 months, I'm doing $100 each month. One important thing here is that you want to make sure that all your units are the same. So if you're talking about 6 months, well then the deposit has to be monthly. It can't be yearly. So you might have to adjust that just to make sure that it makes sense. So just keep that in mind. And then E, my rate is 0.005. And T I'm going to leave, because that's going to be my variable for integration. And then in the end, you'll end up plugging in the 0 and 6 in for that T. So let's go ahead and do our integral. So we're going to keep that 100. You could bring it out in front, but really, it doesn't really matter for this. So I have, remember, when you integrate with E, you keep everything the same, but then you have to divide by that number in front of T. And then I have my bounds, my 0 to 6. And then we can go ahead and divide those out. So you get 20,000 for that. E to the 0.05t. And I have my bounds. And now I'm going to go ahead and plug in. So I have 20,000 e to the 0.05 5 times 6 minus 20,000 times e to the 0.005 times 0. Make sure you don't just cross that one off because now we're dealing with e to the 0, which means it's going to be 1, so that's going to be important. So we're going to have these numbers being subtracted. So this is going to be, type that in your calculator. This ends up just being minus 20,000. And we end up with $609.09. And remember, I'm rounding to 2 decimal places because it's money. If you compare that to what we got on the previous problem, very similar. So again, that shows you that integrals are going to be way quicker to use for this type of problem. And you're getting pretty much the same answer. It might be off a little bit. So if we look at the next problem, it wants us to use the same values, but to look at a 20-year period. So here's a situation where you definitely wouldn't want to go the long way. Plus, when you're doing it that long way, you get more rounding errors because you're constantly rounding those numbers. Where your integration, you're not rounding till the very end. So that's your more accurate answer. So just keep that in mind. That's why we like integrals. So in this case, we're looking at a 20-year period. But notice it says 20 years, not 20 months. So that's the first thing that sticks out to me that we need to take care of. Because remember what I said, all the units need to be the same. So since our monthly deposit's $100, let's just convert this over to months instead. So if we have 20 years times 12 months in a year, that means there's going to be 240 payments. So 12 monthly payments or 12 months. So that tells us there's 240 total payments. So what we're going to do, so again, this is another continuous with interest problem. So we're going to write out our formula. So our future value is going to be the integral from 0 to t of f of t times e to the rt with respect to t. So we plug in, so it's going to be 0 to 240. $100 is the continuous money flow. E, and we are going to use that same rate. And then times t with integrating with respect to t. So we have our integral is going to look very much the same because it's the same problem. So 0.05, keep that exactly the same. And then remember to divide whenever you have, you're integrating with respect, or integrating with e to a power. So we divide by the number in front of t. So there's my integral, and then the only difference here is we're just plugging in different numbers at the end. So I'm going to just rewrite this as 20,000 again, dividing those out. And now we can plug those numbers in. So 20,000 times e to the 0.005 times 240 minus 20,000 times e to the 0.005 times 0. And remember, with this 20,000, you could have left it out in front and then distributed it at the end. So go ahead and you subtract those out, and I'm getting $46,402.34 when I round 2 decimal places. So that's the total amount if this happened for 20 years instead of just 6 months. So it should be significantly larger in comparison to the other part of the problem because it's money flow for a significantly larger amount of time. So we'll stop this video here, and then the next part of this lesson will be in another video, and that will be talking about kind of going backwards. So instead of talking about the future value, we'll talk about the present value.